about sampling theorem. So this derivation was already done in our last class. So how the sampling theorem is defined? It is a band limited signal x of t with x of j omega equal to 0 for mod omega is greater than omega f is uniquely determined from its samples x of nt if the sampling frequency fs is greater than or equal to 2fm. That is, sampling frequency must be at least twice the highest frequency present in the signal, right? Okay. So now we are going to discuss about the Nyquist rate. What is meant by Nyquist rate? It is nothing but the minimum rate at which a signal can be sampled and still be reconstructed from its samples is called Nyquist rate. So it can be sampled and it can be reconstructed. Okay. So it is the minimum rate at which a signal can be sampled and still be reconstructed from its samples is called Nyquist rate. It is always equal to double the maximum highest frequency, that is 2fm, that is Nyquist rate. So it is always equal to 2fm, where fm is the maximum frequency component present in the signal. Okay. So if the signal sample set to greater Nyquist rate is said to be oversampled, and a signal sampled at a less Nyquist rate is called undersampled. Okay, greater Nyquist rate is oversampled, and less Nyquist rate is called undersampled. Okay. Next, we will see the anti-aliasing filter. So, a filter that is used to reject the high frequency signals before it is sampled to reduce the aliasing is called the anti-aliasing filter. A filter that is used to reject high frequency signals before it is sampled to reduce the aliasing is called an anti-aliasing filter. In diagrammatically, it is represented like this: x of t is the input, anti-aliasing filter is there. Then before the sampler, it will be used. Anti-aliasing filter used before the sampler. Okay, then we get the x of n. This is anti-aliasing filter prior to the sampler. Okay. Next, we'll see the signal reconstruction. So, signal initially in discrete time signal is sampled, and we can get the original signal from the sampled version. That is called signal reconstruction. Okay, signal reconstruction. As we already discussed earlier, that a bandwidth signal x of t can be reconstructed from samples if the sampling rate is above Nyquist rate. What is Nyquist rate? 2fm. So if the sampling rate is above the Nyquist rate, then it can be reconstructed. Let the sample signal excess of t with the sampling period 3 seconds is excess of t is equal to sigma n equal to minus infinity x of nt into delta of t minus nt. That is equation number 1. So the Fourier transform of excess of t is given by x of e power j omega is equal to 1 by t sigma n equal to minus infinity x of j into sigma omega minus 2 pi m by t. It was already derived in our earlier case. That is equation number 2. The frequency spectrum x of e power j omega consists of an infinite sum of shifted replicas of the frequency spectrum of the original signal. To get the original spectrum of the signal, excess of t is to be passed through a reconstruction filter with an impulse response h of reconstruction filter is also called as low pass filter. Okay. So that we can get the original spectrum of the signal excess of t. Okay, so excess of t is passed through a low pass filter h of t to get the original signal x of t. The original signal can be obtained by combining the sampled signal excess of t and that impulse response h of t of the filter by convolving, not combining, by convolving excess of t is convolved with h of t, so that we will get the original signal x of t. So that is x of t equal to excess of t convolved with h of t. Excess of t is the sigma n equal to minus infinity x of nt into delta of t minus nt convolved with h of t. Okay. So we can write this as integral minus infinity sigma n equal to minus infinity x of nt into delta of tau minus nt into h of t minus tau 3 tau. Delta of tau minus nt equal to 1 for tau equal to nt and the 0 for tau is not equal to n. So we can write this as x of t is equal to sigma n is minus infinity to infinity x of n t into integral minus infinity to infinity. Here we are changing the order of integration and the summation terms. Okay, delta of tau minus n, n t into h of t minus tau t. Okay, so therefore x of t equals sigma n is minus infinity infinity x of n t into h of t minus n tau. That is equation number 3. The frequency response of the low pass filter can be expressed by h of j omega is equal to t for mod omega is less than or equal to omega s by 2 and is 0 for mod omega is greater than omega s by 2. That is equation number 4. So if it is the frequency response of the low pass filter, it will be like this minus omega s by 2 to plus omega s by 2, its magnitude is t. Okay, so the impulse response of the low pass filter is h of t, that is expressed as 1 by 2 pi integral minus omega s by 2 to omega s by 2 plus omega s by 2 h of j omega into e power j omega t d omega. Or we can write this as a t by 2 pi into integral minus omega s by 2 to plus omega s by 2 into e power j omega t d omega. It is equal to t by pi t. Okay, to sin omega s t by 2 is equal to t by pi t into sin pi t by t, or t by pi into sin pi t by t by t. That is equation number 5. And h of t minus nt is t by pi into sin pi by t into t minus nt by t minus nt. So replace t by t minus nt here. So on substituting equation 6 in equation number 3, we get x of t equal to sigma n equal to minus infinity infinity x of n t into sinc pi by t into t minus nt. That is equation number 7. Here sinc function spreads over entire time axis. To reconstruct the signal at time t equal to t naught, we must know all the sample values, including those for n t is greater than t naught. So it represents a non-causal system. Hence, this type of reconstruction is not suitable for real-time applications. Okay, so it is here the sync function spreads over entire time axis. To reconstruct the signal at time t equal to t naught, we must know all the sample values, including those for n t is greater than t naught. So it represents non-causal system. Hence, this type of reconstruction is not suitable for real-time applications. Okay, therefore we need a different approach. We need a different approach to convert a digital signal to analog signal. Here, a digital to analog converter produces output voltage that is proportional to the value of the binary bar. The output of DAC, digital to analog converter, is applied to an interpolator which converts the output samples of the DAC into an analog signal. There are several interpolators. So here, digital to analog converter is like this. So DAC. So after DAC interpolator is introduced to the output of the interpolator is XA cap T. So after that, they will introduce the low pass smoothing filter so that the signal will be smoothed and get the output as analog output, smooth analog output here. Takes up. Okay. So here there are several types of interpolators are there. So here the interpolators are zero order mode. Now the interpolator is zero order mode interpolator. Okay. See, zero order hold. One of the most widely used interpolator is zero order hold. In this technique, a given sample is hold for an interval until the next sample is received. So it can be hold. So a given sample is hold for an interval until the next sample is received, right? So it is one of the most widely used interpolator. That is a zero order hold. In this technique, a given sample is hold for an interval until the next sample is received, right? So mathematically, it is represented as x cap t is equal to x of n for n t is less than or equal to n is less than or equal to n plus 1 into t for n equal to n where n is 0, 1 to up to n. In particular, x cap t is equal to x of 0 for 0 is less than or equal to t is less than x of t for t is less than or equal to small t is less than 2t and x equal to 2t for 2t is less than or equal to t is less than 3t. That is equation number 9. So here zero order code. So zero order code interpret is here. This is x of n t is given as input for this one. So its output is x cap p. So it can be represented like steps. Okay, you can hold for an interval until the next sample is received. The impulse response of a zero order hold is given by h of t equal to 1 for 0 is less than or equal to t is less than or equal to t and is 0 otherwise. That is equation number 10. Okay. Then coming to the transfer function of a zero order hold, the output of zero order hold is expressed in terms of h of t. That is, the output x cap t is the convolution of x of n t and h of t. Convolution of x of n t, that is discrete time number. And combined and this simple response h of t. So x of n to h of t. So x a cap t is equal to sigma n equal minus infinity x of n t h of t minus n t. That is equation number 11. Here h of t in equation 10 can be expressed as h of t equal to u of t minus u of t minus n t. That is equation number 12. So in general h of t minus n t is okay, u of t minus n t minus u of t minus n t minus n t. Okay, so t minus n plus 1 into t, that is equation number 13. On substituting equation number 13 and equation number 11, so that we get x cap t equal to sigma n minus infinity x of n t into h of t minus n t is u of t minus n t minus u of t minus n plus 1 into t. Taking Laplace transform on both sides, we get the Laplace transform of x cap t is equal to sigma n minus infinity x of n t to Laplace transform of u of t minus n t minus u of t minus n plus 1 into t. Okay. So that it is equal to sigma n is minus infinity x of n t into Laplace transform of u of t minus n t is e power minus s n t by s minus u power t minus n plus 1 t is e power minus of s into n plus 1 t by s. Okay. So it is 1 by e power minus s t by s into sigma n equals 0 to infinity x of n t e power minus s n t, or it is 1 minus e power minus s t by s into x cap of s. Okay. X cap of s. Okay. So it is equal to xa of s by x star of s is equal to 1 minus e power minus s t by s. Therefore, the output of zero order field consists of higher order harmonics. So now these harmonics of the output of zero order field is applied to a low pass filter as shown in figure 1. This filter is often called a smoothing filter because it tends to smooth the corners on the step approximations. Okay. So now we will do a problem. Find the convolution of two finite sequences given below. Also verify the result by using pressure or method. So x of n is given as 2 for 0 is less than or equal to n is less than 3, it is 0 otherwise. And y of n is given as y of n is given 1 to 3 to 1. So yeah. So x of n can be written like this: x of minus 1 is 0, x of 0 is 2, x of 1 is 2, x of 2 is also 2. So x of n can be written as x of 0, x of 1, and x of 2 components to group. So that y of n is y of minus 2 is 1, y of minus 1 is 2, y of minus 1 is 1, y of minus 1 is 2, and 0. Y of 0 is 3, y of 1 is 2, y of 3 is 1. Right? Right. By replacing independent variable n by dummy variable k in x of n and y of n. So it will become x of k equal to 2 to 2 and y of n is 1 to 1. And now h of n is convolution of x of n and y of n, that is sigma k equal to minus infinity into x of k into y of n minus k. So h of n equal to sigma k equal to 0 to 2 x of k into y of n minus k. Okay, that is equation number 1. Now expand equation number 1, we get h of n equal to x of 0 into y of 0 minus k, that y of n minus 0. So that is y of n x plus x of 1 and y of n minus 1 plus x of 2 into y of n. So y of left hand side of left hand of h of n equal to left hand of x of n plus left hand of y of n. So what is left hand of x of n? Left hand of x of n is 0. What is left hand of y of n? Minus 2. Okay. So 0 plus minus 2, that is minus 2. Similarly, right hand of h of n equal to right hand of x of n plus right hand of y of n. Right hand of x of n is, see, right hand of x of n is 2. Similarly, right hand of y of n is also 2. 2 plus 2, 4. Okay. So that is h of n got to be completed from minus 2 to 4. Minus 2 only for n equal to minus 2. H of minus 2 is minus 1 is 6. H of 0 and will get minus 2 to 4. This is about the convolution of finite sequences given below x of n and y n, right? This is